folks. Okay, so it is the long-awaited Chapter 4 Part 3 video. I'm so sorry that it's taken so long to get it to you guys. I looked at actually my notes for this chapter and I wasn't very thrilled with them. I didn't feel that they were clear enough, and I know that there are some that are struggling a little bit, so I wanted to see if I could polish them and make them a little bit more clear. I'm very sorry it took so long. Any case, before we were talking about rings, and we were talking about the strains of rings, okay? But before I get on and sort of continue that ring story, there is something also having to do with rings, actually, that I needed to sort of back up and mention to you guys. Okay, so this is called cis-trans relationship. Okay, and quite simply, it's actually it's not a very complicated idea. But if you have a ring here, yeah, and each one of those atoms are we're talking about cycloalkanes, so each one of those atoms are sp3. Then let's say we take the ring and we know that it doesn't like to be really flat, but for the moment we put it flat. The things that are on there will be things that are on the same side of the ring. Okay, you know, maybe they're both up, or they're both down, according to this ring, that imaginary ring I'm holding in my hand. Okay, or there are things that could be on opposite sides of the ring. Okay, imaginary ring right here. Okay, all right, and if they are on the same side of the ring, that's called cis. Sisters like to hang out. There you go. You're welcome. Anywho, and then when they're on opposite sides of the ring, they're not together, that's called trans. Okay? So that's not too bad. Okay. So let's just draw them flat, yeah? Okay. CH3. This in OH. Those substituents are cis to each other, same side of the ring. Okay. Another example. Let's make a 6-membered ring. Okay. Okay. There's an isopropyl, and there's a methyl. Those are also cis. They're on the same side of the ring. You know, held fixed from the perspective of being fixed on our board, even though we know in real life they float around and stuff. These are sticking out at the camera, at you guys in this room here, and these guys are sticking into the room next door. Okay. Okay, and then like I said, trans is just going to be on opposite sides. OH again, and let's make that chlorine. And then 5-membered ring again. Okay, and I don't know, we can make this a T-butyl. Okay, and that will be an amine, NH2. Okay? Trans to each other. All right. And you could take one of these and say, well, what if you had the molecule, what if we took this molecule, what's the relationship between this molecule, okay, and this molecule, okay? You guys think about that actually in the most general sense. What is the relationship between those two molecules? Okay? You know that they're going to have the same molecular formula. They are indeed different compounds. If you're a little bit unsure of that, they are definitely different compounds. Okay, and I'm going to talk about differentness in the next chapter. But those are different compounds. Okay? So they are isomers of each other. And this is not the constitutional isomer that we've talked about in previous chapters, where you have different connections between atoms. This is actually a new type of isomer called a stereoisomer, which again, stereoisomers and stereochemistry is the subject of chapter 5. Okay? Okay, so yeah, in any case. All right. So back to the, well, I got these up here actually. Thinking back to the strain issue, we know that some rings, not actually cyclopentane, some rings can experience some rings, some angle strain. Okay, that's the deviation from 109 degrees, 0.5. All right. And then you can also have a lot of eclipsed things coming off the hydrogen, experiencing, if they're just hydrogen, experiencing torsional strain. Okay. On this guy here, there are unwritten hydrogens, right? Okay, and then if you look down that, it's just like what we did with Newman projections, where those bonds, remember, they're big and fluffy. They're not actually lines like we draw there. They're big and fluffy, and so they get to each other and they have a repulsive interaction. Okay, so yeah, so what do these rings do so that they alleviate that? They don't stay flat, in the simplest way of saying it. And to different degrees they pucker. Okay, they're as drawn on the board, flat like that. They're all in the same plane. Okay, well, they're going to with different strategies for different rings. They're going to put one of those carbons out of the ring. Okay, for cyclopentane, what it tends to do is just take one of the carbons and pops it out and keeps the other 4 in the plane. That alleviates 6 torsional interactions. Okay. Remember, there isn't a lot of ring strain with cyclopentane, so it's not a big problem there. And then it tends to just alternate sort of around the ring. Okay. So 4 of them tend to the most common configuration is 4 of them are in the same plane and 1 of them bends out of the plane either direction or whatever. Cyclobutane. If you think of having like a box here and I could grab 2 opposite carbons of the box, okay, it tends to come together like that, like sort of flap together, almost making a taco kind of. Yeah, and then in a minute we'll get to the most interesting sort of the main story of today's production, and that's cyclohexanes. Okay? All right, let me finish erasing this guy and put some text up here for you. Okay. All right, so my notes, I pray this agrees with your notes. I am on section 5, part B. Okay. Different ring sizes leads to different strategies. Okay. As I said, cyclobutane. Okay. They tend to do that's me trying to draw out where 2 of them on opposite sides, not the 2 next to each other, because yeah, well, I guess you could fold like that, but the most common is sort of doing that. Okay. Now, if you were to sort of sight down, pick 2 carbons to look down and see if there's any sort of bad torsional interactions or whatever. Got that there, got that there. So now those hydrogens are staggered, okay? Alleviated the problem, so to speak. Okay, and cyclopentane. One corner alternating, this isn't a well-crafted phrase here, but I think you'll get it. Alternating flips up, let's say. It's really not a well-written phrase, sorry. Okay, so so that's one, you have a 5-member ring, that's one size folding up. This configuration is sometimes called an envelope configuration. Okay. And as with cyclobutane, now if you to look down, okay, you'd see that, oh, okay, those hydrogens are no longer sort of in a torsional or an eclipsed, I should say an eclipsed configuration, experiencing torsional strain. They're nice and staggered, and everybody's happy. Okay? All right, that brings us, okay, guys, big story. It's toy time. Yay. All right, so this is cyclohexane. And what's kind of funny about these two is if you build them and then you try to make the ring flat, it actually doesn't want to really be flat. It wants to kind of tweak and twist. So it mimics the real thing in that way. All right, so what is cyclohexane going to do? Kind of like what I was describing with cyclopentane, is one carbon's going to pop up, but a carbon on the opposite side is going to pop down. Okay, so watch what happens when I do that. All right, there you go. And that creates what we call, it was named the chair configuration. Okay, and just because you maybe imagine sitting on a chair, here's where your rear end goes, and there's where your back goes, and your feet go over the end there, yeah? Okay? All right, and when you have a chair configuration, it actually creates two distinct type of positions on each carbon, okay? There are positions that sort of run vertically, okay? And those are called the axial, and I color-coded those for you. So those are all, well, it's not really pink. What is that? Let's call it pink. Okay, that's pink, all right? And so they're running vertical, all right? And then sort of all along the perimeter here, those are running horizontal. The ones running vertical are called axial positions, and you can remember it easily because think of like the axis of the Earth. Okay, our Earth spins on an axis, right? And then these ones here that go out sort of horizontally, those are called equatorial positions, much like the equator of the Earth. Okay. All right. Now, as it happens, okay, things that are yeah, maybe I'm getting ahead of myself. Yeah, I am getting ahead of myself. So hold on just a second. All right. When these, what these chairs can do now, sorry, is they can sort of change the little tweak that they just made. Okay, so that this carbon can now pucker the other way, and this one can go the opposite direction. Okay, so it goes like that. And it will. I mean, not only can it do it, but it will, okay? And so we tend to call that a chair flip. The chair flipped, see, we got a chair again, okay? Now, here's a really cool thing about a chair flip, all right? When we did a chair flip, all right, all the things that were in the axial positions, the things that were running vertically, okay, switched to equatorial positions. See how all my pink bonds are now in the equatorial positions? And all the things that were previously in the other flip in the equatorial positions have now gone into the axial position. See, straight up and down, straight up and down, straight up and down. All those right there. Okay? All right. Good, good, good stuff. Okay, now let's talk about, I mean, that's about the end of the story, until you start thinking about cyclohexanes that are substituted, that have a substituent, something sticking off it. Okay, so let's look at that. Okay, so this is what we have here. This is just a methyl group that I have added to our, let me make it flat again, maybe that'll be better. Okay, just added one methyl group, okay, one CH3 to the cyclohexane, okay? And now let's do the flip deal, okay? So there we go. The methyl group is in the equatorial position, okay? And then if it flips the other way, and it will at room temperature, okay? It's an equilibrium process, all right? Now that methyl group is in the axial position, okay? And yet again, as we've seen in this chapter, this is another place where these little sticks and these little lines and stuff don't do the volume of these atoms justice, okay? As it happens, a general phenomena for chair configurations is that having substituents in axial positions is destabilizing, okay? Mother Nature would rather have this chair in the other flip form where the axial substituent is in the equatorial, okay? So equatorial is better, more stable. Mother Nature likes it better. Mother Nature wants the big things. If you've got lots of substituents, Mother Nature wants big things in the equatorial positions, okay? At something like this, at room temperature, it's still going to go back and forth. But again, it's like other equilibriums we've looked at, like weak acids, where which side of the equilibrium is favored. If you could freeze time, what are most of the molecules in the population doing? Okay. And in this case, most of the molecules, or some type of majority, you can actually do calculations. We won't do that. But some percentage of the population will have it in the axial position, but some majority, the higher percentage of the population will be in the have this in the equatorial position. Okay. Now, why is it bad to be in the equatorial or in the axial position? It's because, again, these have much greater volume. These have greater volumes, and something in an axial position starts to have a steric interaction. Remember, steric is things banging into each other. Okay, it starts to have a steric interaction with whatever's in the axial position 3 carbons away. Okay, so here's this carbon, 1, 2, 3. Okay, and then 1, 2, 3. Okay, and so this substituent is banging into those things that are in the axial position 3 carbons away. Okay. These carbons that have these axial positions that are 1 atom away, they're on the other side of the ring. Okay. All right. Okay. Let me put some stuff up on the board. Playing with the toys too much. All right. C. Cyclohexane. Okay. Cyclohexane. Kinda most important. It's kind of the most important of the rings that we're talking about in terms of what they do. You can also say that it's perhaps the most important actually in biology. Of all the rings in biology out in our structures out there in the world, it's the most common. It and five-membered rings. Five-membered rings are very common as well. All sugars, okay, carbohydrates, are predominantly in a six-membered ring or five-membered ring. Okay? DNA tends to have six-membered rings and five-membered rings. Okay, so and the chair strategy, which I haven't even talked about yet, other than my little jibby jab up in front of you. Makes it the most stable. That's something I didn't really make clear when I was showing you my toys, is that that chair configuration, I should have done that, shoot, I could do it in a little bit, but that chair configuration, every single torsional interaction, and if you put it flat, there's a lot of torsional interactions, right? As soon as you make that chair, they're all gone. Every torsional interaction around the ring is now staggered with respect to each other. Okay. The bond angle is also, I forget actually, honestly, what exactly the bond angle is, but it's very close to the desired 109.5 for sp3 carbons, or sp3 atoms. Okay. Very common in nature. Okay. And the chair strategy is its most common. It's not the only thing actually that that cyclohexanes can do. They can do others. They can do something called a bow. Sorry. But chairs are much more common. Okay, so now one of the things in order to absorb this material, it's a good idea to get some practice with learning how to draw these chairs. And I put a handout up and I sent out an email, and hopefully you guys were able to get at that and give that a try. Yeah, so let's look at just kind of recreate on the board what I demonstrated for you. Shucks. What I'm trying to draw is a cyclohexane that's flat and kind of a little bit on its edge. Okay. All right. And so if you, this is flat. Okay. And if you look at these tips here, all right, and one of the tips you bend up, so that tip flips up, all right, and then that tip flips down, okay, we will have created, so the way you draw these is you put two, is that going to be okay? Yeah, that's going to be okay, I guess. Put two lines that are parallel but askew, okay, so one shoots past, in this case the top one shot past and the bottom one went that direction, okay? So you do that first, all right? And then you draw a 90-degree angle off that guy, 90-degree angle off that guy. All right. And now I can draw in the axial positions that I was discussing. Okay, the vertical ones. Right. And then I want to use blue. Where's my blue? So sorry. Normally try to avoid green, but let's give it a try. Okay, and then my the equatorial positions. These are pretty easy. You just go to these different. You start at one of the tips, draw straight up, or in this case, straight down, and then you alternate up, down as you go around the ring. Okay. The equatorial is a little bit trickier to figure out what angle you should do. What you do is you're going to draw. I'm going to come here. I'm going to draw an equatorial. I'll just draw it in and tell you how I went about doing it. Okay, there's that guy. What I did was I drew him parallel to that line and that line. Okay. Remember, these lines are parallel, so the process of drawing that, if I made it parallel to one, I made it parallel to the other. Okay. So, and I forget actually, to be honest with you, on that handout how I described it. I've always had a little bit of trouble coming up with a good way to express it. You're drawing it parallel to a bond that's 2 bonds away. So you're drawing it parallel, not to this obviously, and not to that, okay, but 2 bonds away there, all right? Or you're drawing, so now I'm going to come to this one here. What one am I going to draw it parallel to? Not this or this, but this guy, okay? Which, by the way, because of that process that we went through drawing the original ring, that one is parallel to that one, okay? Okay, and then this one here goes like that. This one there goes like that. That one there goes like that. And there we go. Okay? All right. Let's put in some hydrogens around this guy. All right. H, this is bar none the most colorful chair configuration I've ever drawn. It's like a Christmas tree, something. Okay. All right, and then I'm going to label this here, all these as AX for axial. Okay. You notice I go around the ring, it's going to be axial up, axial down, axial up, axial down, axial up, and axial down. Okay. All right, and then on all the equatorials I'll draw EQ. Okay. You can kind of, and this is going to be helpful in a minute, you can almost sort of look at like, let's take this equatorial here. That's somewhat down. Okay, you might be like, oh, what do you mean down? A little bit easier to see the up and down when you're talking about the axial dudes. Okay, but certainly this bond, if this bond is up, that one's down. This is more downer than that guy. Okay, and then this one is up compared to the other bond on this carbon here. Okay? Being able to look at those bonds on your chair configuration and sort of look at them as up and down can sometimes be helpful as a double check when we go to try to draw the flipped configuration of one of these. All right. Okay, so equatorial up, equatorial down, equatorial up, equatorial down, and equatorial up. Okay? All right, there you go. That picture's a little bit busy, but... All right, so I thought the most efficient way to sort of deliver this stuff is I'm actually going to make, yeah, I better erase this. I'm going to make a list, pause if you want. Okay. I'm going to make a list of just facts, okay, about the chair configuration, most of which I have already told you about when I was demonstrating with my little toys there, okay? Oh, there's my blue. Okay. All right. Facts about chairs. Okay. There are two types of positions. Okay. Axial and equatorial. All right. And so I'm going to, from now on, as I did actually in that picture there, I'm going to abbreviate the axial as AX and the equatorial as EQ. Okay. All right, so axial is vertical. Okay. Equatorial is horizontal. Another fun fact. Fun fact. It's better, all right, more better, in other words, more stable to have substituents in equatorial positions. Okay. Chair flip. Okay. The points. Okay. Go up and down. Okay. Sort of switch positions. Okay. Real quick, what do I mean by the points? So you see here the one that I've flipped down, and this might actually be easier to see without the methyl group on there. Be right back. Oh, it's coming all the way. Okay. All right. So this is the guy we flipped down. This is the guy that we flipped up. Okay. What did I call those there? I called those points. I also often call these the tips. Okay. Now to go to the other chair configuration, this is sort of a tip, and this is sort of a tip. Okay. And so that will, one will flip down and one will flip up. Okay. So when we go to draw these, just a helpful little strategy that I use is I always say that when you've drawn one chair configuration, now you want to draw the other chair configuration, it's flip configuration. Tip stays tips, okay? So here, this tip stayed a tip, it just went down. This tip stayed a tip, it just went up. Okay? All right. When you get a chair flip, all right, all axial positions become equatorial. Okay? And when flip, all equatorial become axial. Okay? Sorry, so sorry. If we have two substituents on these rings here, okay, just like in any ring, like I showed you at the very beginning of this lecture, you can have them on the same side of the ring, okay, or you can have them on opposite sides of the ring, okay, that cis-trans relationship. And in the process of a chair flip, the cis-trans relationship will not change. It doesn't, and it makes sense if you think about it, because in order to change, or they're both sticking this way, you'd have to actually break a bond, take a hydrogen off, and plug it back in. Okay, so even though these things are flipping, if they're cis over here in one, they're cis over there in the other. Okay, oops. Maybe I should show that. Okay, so you know, who knows what they are? We don't need to specify, but I put those two guys in a cis relationship. They're on the same side of the ring, right? Now, let's do a chair flip. Okay, we didn't break any bonds, so they are still on the same side of the ring. I didn't do a very good flip. Okay, there we go. All right. And by the way, this chapter is one of the whole reasons we recommend that you guys buy these so that you can play with these. Sometimes some of us have a harder time getting used to looking at things in 3D and stuff like that. So what's interesting is that note that they're cis, right? This is in an axial position and this is in an equatorial position. Okay? Now, if I move it, that's if they're 2 carbons away. If I move this cis guy, and I put this cis guy, and I keep him cis, okay, still on the same side of the ring, now they're both in axial positions because they're 2 carbons away rather than 1 carbon away. All right. Okay. But one thing that doesn't change, okay, is, let's go back to the other one where one is in equatorial, the other is in the axial. Okay, there. Still cis, okay, still same side of the ring, but when we put it in the chair configuration, okay, as I said, we just got equatorial, this guy's axial, okay, but they're both up. And again, up is arbitrary, right, because this is really a molecule floating all around and stuff. But in order to sort of visualize these chairs, it's nice to just keep them fixed in our mind. And when they're fixed in our mind, you'll notice that they are both up. That is the more uppy position on that carbon. That is the more uppy position on, oops, you can't see. That is the more uppy position on this carbon, okay? All right. And then, okay, so if for a chair configuration, if you have a cis arrangement, okay, they will both be either up or they can both also be down, actually. Wow, look what I just did there. That's not a chair flip, all right? Notice this was axial a second ago, it's still axial here. I just rotated this molecule, okay? So if this is the way we decided to fix it, you know, either holding it or on a board, then now we could look at it and say, okay, well look, this guy's down, that guy's down, they must be cis, okay? This is the downy position of that carbon, that's the downy position of that carbon. So they're on the, they're both down, so they're both cis. All right, now if you have trans, okay, it's just sort of the opposite story. All right, one, again on a fixed chair, one will be up and one will be down, okay, for trans, okay? All right, let me finish my list. All right, finishing with the list. What do I got? Okay. Flipping. Doesn't change cis, trans, trans relationship. Okay, just like we just went over. If they start out trans, flipping ain't gonna change that. If they start out cis, flipping ain't gonna change that. Okay. Okay. Can be helpful to see each position as up or down. Okay. Finishing over here. During a flip, okay, up, down, doesn't change. Okay? Remember when we were going through, we were, okay, this one's more uppy, this one's more downy and stuff like that. If you flip it, it'll stay up. Okay? And that's, you know, different from what happens with that equatorial, axial equatorial type of relationship. In a flip, everything that was axial becomes equatorial, everything equatorial becomes axial. Okay, so when we are in a moment tasked with trying to draw one and then draw its flip, okay, we can make sure that everything on this one that was axial became equatorial and everything that was equatorial became axial. And we can double check that by saying, all right, was everything up that was over there? Did it stay up over here? Okay, it's over on this wall. Okay. Cis substituents will be either both up or both down. Okay? Trans substitutes, okay? One is up and one is down. Okay? All right, so that's the end of my fun facts. I guess here. All right. Yeah. I want to real quickly, okay, I got drew one past. And I always make this mistake. I always make them two angled. They're parallel, but they're two angled. It's going to make a better picture if I make them a little bit flatter, just a slight angle. Okay, so yeah. Huh? Did I make it any different? Maybe it's flatter. I don't know. I'll stop. Okay. All right. And then let's put in all our bonds. Okay. All right. I should have done this more systematically. Axial up, axial down, axial up, axial down, axial up, axial down. Okay. Equatorial parallel to that, equatorial parallel to that. On this guy here, equatorial is going to be parallel to that. Equatorial here is going to be parallel to that. This equatorial is going to be parallel to that. Okay. And that one is parallel to that. But not really the way you do it. Come on, dude. Alright, there we go. Okay. I want to put in a chlorine. Okay. And then I'm also going to put in a bromine. Okay. And then I'm going to put in a CH3. I'm going to put in all the hydrogens that I'm missing. I'm not going to make this quite as crazy colorful. I felt that was busy. Okay. All right. Now, just in case that kind of up-down business stuff isn't all that clear, so, you know, that's up, that's down. This chlorine, again, it is arbitrary because this is floating around, it's molecule floating all around the world, but fixed on the board so we can keep track of everybody's relationship. It's good to think about up and down in this fixed position here. So that's up. Okay. Actually, I'm just going to try use. All right. That's up. That's up. The bromine's up. This one is up, and that one is up. Okay. And then this one is down. 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 Okay. All right. All right. So I want you to think about for a second: is the system is the CH3 and the bromine are those trans or are they cis? Okay. Are the halogens, the chlorine and the bromine, are they cis or are they trans? Okay. Oh, hey, oh, hey, come here, give me the pen. Okay. Yeah, I'm over here. Okay. So Br and chlorine are both up. Okay. Same side. Okay. Cis. All right. Bromine is up. Okay. CH3 is down. Okay. So opposite sides. Okay. Trans. Okay. Is that too low? Can you guys see that? You guys can see that. Okay. Cool. All right. Now, I'm going to sort of tie together, there was a random fact, I didn't explain all of them, although they're reiterations of when I was doing the toys in front of you. What I'm going to do now is I'm going to do a typical problem, and then in the process of the problem sort of point out random facts from our fun facts and explain some of them. Okay? All right. Let me get a nice fresh board. Oops. Okay. All right, exam. Okay. Please draw chair config of, oh shucks, please draw both chair configs, okay, one chair and then its flip, and decide which is favored, okay? All right, so let's draw it flat style. Okay. All right. There's more than one way to do this type of task. Okay? And some of the decisions on getting started are totally arbitrary. Okay? They are the types of things, once you make those decisions on those arbitrary decisions on how you're going to get started, then they lock you in down process. Okay. But yeah, so I'll show you, over the years I've developed just, kind of how I do these problems, just some simple rules. Even though it's kind of arbitrary, you could just do it the way that I do it. Okay. The first thing that I think is really helpful is you want to number the ring, okay? And we talked about how to number things like this when we're naming cycloalkanes. Okay, on one that's like this is called 1,3 substitution. There's one at 1 carbon and then 3 carbons away. When it's 1,3, you can't do that position lowest sum game that we were playing to decide what's 1 and what's 3, because 1 and 3 makes 4, 1 and 3 makes 4, same, so it doesn't help. So you go by alphabetical. That is isopropyl, that is methyl, so isopropyl comes first. And for the process of making chairs, you don't actually have to do that, but I just thought I would take a chance, or take an opportunity to remind you of that. All right, so 1, 2, 3. All right. Okay. Now you just want to draw one of the chairs. All right, so I'll draw the one that I've been drawing thus far. Okay. And now you want to number the ring, okay? And this is totally arbitrary. I don't even have some rule that I normally go by. I think I often make this one 1, but whatever. At this point, it don't matter. Once I've numbered it, and then I go to do this guy here, it's going to matter, okay? But numbering the first one doesn't matter. All right? Okay. All right, so that's exactly what I'm going to do. I'm going to do 1. And then I think I will go, I really struggle with clockwise and counterclockwise. I just looked up at a clock. I'm going to go clockwise. 3, 4, 5, 6. Okay. All right. Now, again, as it happens, when you put in that first substituent, it's actually arbitrary whether you put it in the axial or equatorial position. Okay? As long as you don't screw up this relationship. And what is this relationship? Trans, exactly. Good job, guys. I just never tire of these dumb jokes. Okay, so it's arbitrary how you first do it, but once you put in any other substituents, once I put in this case, just the second substituent, you need to not break that trans relationship. Okay? My personal way of doing it, and whatever, I tend to, if it's a wedge, when I put it in, I put it up. And if it's a dash, I put it down. Okay? So let's try that. Again, that first substituent, totally arbitrary. But I got my rule. Let's go blue. Okay, so wedge up, and on carbon one, oh shucks. What are you doing, Burr? Oh, I'm sorry, folks. I'm sorry. I'm so sorry. I lied. Inexplicably, I didn't number this one this way. That's the correct way you number it for naming. We're not naming it here. And I don't want to mess up the rest of my picture, or I would change on the spot here. But I'm going to keep consistent to my notes. Precious stuff. Spent a lot of time working on it. All right. So carbon one, wedge up. On that carbon there, up is the axial position. Okay. CH3. And then on carbon 3, that's a dash. I'm going to draw it down. Okay? Down in that position is equatorial. Okay? Notice I've maintained my rule here. They're trans, so one better be up and one better be down. One's up, one's down. All right. I want to draw in the missing hydrogens. Okay. All right. And I want to do that because I want to remind you the reason axial is destabilizing, okay, is steric interactions, okay, with axial positions 2 carbons away. Okay. This is called 1,3 diaxial. That's just the name for this particular interaction, which again, these pictures don't do them justice. They're much puffier and much closer. Okay. 1,3 diaxial interactions. Alright, lovely. Okay, now, how the heck do we draw the next one? Here's how I do it. You can just memorize how to draw the 2 different flips. But the way I do it is those first 2 lines, I tend to draw them at the same angle, but I reverse the askew. Okay, so whereas this top one shot past and this bottom one came under this way or whatever, however you want to say it, came to the right, blah, 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 I switch that trend. Okay, so on this guy, oop, that's too flat. On this guy, And then that guy. Okay? Alright. And then I'm going to draw that 90. I'm going to draw that 90. I'm going to connect my dots. Okay? Alright. Now I want to number this one. Okay? Keeping all the relationships and the positional information that I have over there consistent. And the easiest way I have found for my personal own usage here is to, I do that thing that I talked about earlier, tips stay tips. Okay? So that's Tibby, that's Tibby, okay? That tip, I'm going to grab that one and I'm going to yank it down, that's that tip. Okay? This tip here, I'm going to yank it up, that's that tip. Okay? Alright, so what carbon is that? Yes, carbon 1. Okay? Be very systematic about this. Don't cheat, because you can get a little bit. I think some of the mistakes I've seen over the years and stuff. People maybe think this is 2. Okay. So now I'm going to start. What carbon is that? All right. That's carbon 2 actually. That guy right there. All right. If he's 1, and if I'm going to go clockwise, okay, then that's got to be 2. Which means that's 3, and 4, and 5, and 6. Okay? Now I'll draw in the substituents, all right? Remembering that axial becomes equatorial, and equatorial becomes axial. All right? So there's a CH3 on carbon 1. There's going to be a CH3 on carbon 1. It was axial, now it's going to be equatorial. Okay, draw that line parallel to that guy, sort of, not really, River. Okay. And then I'm going to go over to carbon 3. Maybe that's when people screw up a lot. They don't realize that that's, I don't know. Okay, equatorial becomes axial. Right there, axial does that. Okay. And note, by the way, that getting carried away again with the colors. Okay? Is this up or down? According to the convention. That's up. Alright? Over here it's up. Up stayed up. This guy is down. Down stayed down. So nice double check. Okay? Now, which one of these is more stable? There's an equilibrium, flipping, 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 flipping. Oh, I'm so sorry. Which one of these is favored? If you could stop time, the population, which one would it favor? Or if you could follow one and follow it over the course of its life, which flip configuration would it spend more time in? Left or right? Okay. Hopefully you paused it, figured it out, and you have decided that this one is the more stable. I don't know what's wrong with me. Okay. If you look at these, they each have one axial position and one in the equatorial position. Sometimes you'll get easy problems where, oh, there's 3 things in the axial position over here and nothing everything's over in the equatorial position over here. That's easy. Okay? Remember, equatorial, more better. Axial, more bad. All right? Here it's kind of tough because each of them have one substituent in the axial and one substituent in the equatorial. Okay? Axial, equatorial. Axial, equatorial. So what's the deciding factor? You remember you want the big things in the equatorial position. So you need to decide what's bigger, CH3 or an isopropyl. Okay? We draw it in this nice compact shorthand, but don't forget, isopropyls are gigantic compared to a methyl. Okay? So that means putting the isopropyl in the equatorial position is going to be more important, and sacrifice and put the methyl in the axial. So this is 1 axial CH3 and 1 equatorial isopropyl. Okay. This is 1 axial isopropyl and 1 equatorial CH3. Okay. The axial isopropyl is bigger and worse, okay, than axial CH3. Okay, therefore, oh, I forgot that I wanted to be able to label this A, and I wanted to label this guy B. Okay, so therefore, A is more stable in favor. That's it. That's it for 4, guys. Okay, sorry again, it took a while to get this out. Hang in there, guys. I promise you that we are going to get through this. It's been a bumpy road for everybody, bumpy road for you guys, bumpy road for me on this end and stuff. We are going to get through this. Do not give up. Keep working. Keep doing the homework. Keep watching the videos. Okay, guys? I promise you. Even if I know some folks are going just fine and stuff. But I know some folks, especially this online business and stuff, it's difficult. I promise you I'm going to take care of you if you don't give up. Okay, bye. Sorry.